All right, so this video we're going to talk a little bit about mass spectrometry. So what is mass spectrometry? It's a measurement of ions. Specifically, what we're going to talk about are positively charged anions or cations. Right? So mass spec is going to measure cations, organic molecules with plus charges. So it's not a type of spectroscopy. It's not radiation. It's spectrometry. It's a little different. And the way this is going to work, we're going to make these cations, things with positive charge we're going to detect, and because they're charged, they're going to be influenced by an electronic and magnetic field. And that's what's going to allow separation. So what happens in a mass spec, essentially, is we have an electron beam, for the type of mass spec we're going to talk about, electron beam. And what's going to happen is this electron beam is going to shoot electrons at a molecule, and that's going to knock out an electron from that molecule, creating a cation. So you have a molecule that's going to get hit with an electron beam, and that's going to cause the molecule itself to lose an electron, and that's going to create a cation, and that's what we detect in a mass spec. So here's what a mass spectrum looks like. A couple things you need to know. The far right peak is called the molecular ion, and that usually is the M plus peak. That's the molecule, right? The molecule with only one electron. So without one electron. So that mass is the same. Electrons are really, really small. So I always think about, this molecule is kind of getting into a brawl, getting into a fight with this electron beam. And the first thing the electron beam is going to do is shoot an electron at it. It's going to knock out a tooth, right? And that's like one electron being knocked out. But if I lost a tooth, that really doesn't change my mass, right? So if a molecule mass was, in this case, 46, right? Losing one electron won't cause it to really change its mass, right? Electrons don't have much mass. The base peak is the largest peak in the mass spec. That's the largest peak, and it represents, right, the most stable cation. Right? So what happens is the most stable cation. What happens is the molecule goes in, the electron beam knocks out one electron. That gets us the M plus peak. See, the molecule's lost one electron. And then that molecule starts breaking up even more, right? So it starts breaking up even more to make more stable cations. Now you can remember, how do we stabilize cations? How we stabilize carbocations? Hyperconjugation, pi bond resonance, and lone pair resonance. So this base peak is the most stable cation, right? You can think about it almost like the most stable carbocation even. And that's because it must be stabilized by one of those ways. And so that's the fragment we see the most of. That's the largest because it's the most stable cation. Molecular ion is just minus one electron, right? So it's still the normal mass of the molecule. The base peak is the most stable cation as it keeps breaking up. So let's take a look at what this looks like. All right, so how does this look actually when we talk about these fragments? What actually happens here? So let's look at two examples. First example is no heteroatom, just an alkane, and the other one's with bromine. So the first thing that happens is the electron beam knocks an electron onto each of these molecules. So the way I like to draw that is just literally a single-headed arrow, because one electron, right? So one electron. And what that does in this case, we don't know where that electron got knocked out, but we know that it did. So we say dot plus, right? So we have a missing electron. And this would be the molecular ion for this molecule, right? The far right peak. Because we only lost one electron, so that's the same mass as we had before. Now what else is going to happen here is this molecule is going to break up even more. And we need to think about ways to break up to make a really stable carbocation. So one way it could break up is, what if this left, right? That carbon there left. So if this fragmentation would end up with a plus charge here, a secondary carbocation, and we end up with a CH3 dot. So where did that come from? So we have a radical at this point. Right, the electrons are going there with that. So this is going to have a plus charge. So the plus charge from up here ends up on the atom that lost electrons. And these, as this bond breaks, this becomes the radical. That radical ends up here. So we want to make the most stable carbocation. So this might be one of the base peaks. We don't need to worry about rearrangements with these. Now, how would this look like with a bromine? It's a little easier with a heteroatom. We can actually see it. The electron comes in, and it's actually going to knock out that electron right there, one of the heteroatom lone pair electrons, is going to get knocked out. So it's a little easier to see, I think. So now there's a plus charge there, right? Because the bromine lost an electron, it got knocked out. You can imagine a bromine's not very happy with that. So this is going to fragment some more, even though this would be, of course, the molecular ion, right? The farthest right peak, the heaviest peak. But it's going to fragment, and maybe the base peak would be something like this, right? It'd be more stable than having a bromine with a plus charge. This might be our base peak, meaning it might be the most abundant fragment, the most abundant cation we'd see. So another interesting phenomenon, besides that kind of mechanistic, how we get the base peaks, and we're, of course, always thinking about carbocation stability, and just make sure you know how to do that stuff. We have another thing about isotopes. So isotopes also play a role here. Isotopes, specifically chlorine and bromine. So chlorine isotopes on this planet, chlorine-35, they exist in a 3-to-1 ratio with chlorine-37. Bromine has an isotope of bromine-79 and bromine-81, and they exist in a 1-to-1 ratio. So the 79 and 81 just means these have more. 37 here has 2 more neutrons. 81 has 2 more neutrons, and they exist in a 1-to-1 or a 3-to-1 ratio. And you need to know this. And what it's going to look like, if you look at a molecule or a mass spec that has these, the molecular ion or any peak that has a bromine, then it's going to have essentially an M plus peak, which you're used to seeing for the molecular ion, and then an M plus 2 peak, and those peaks are going to be in exactly the even ratio. If it's chlorine, they're going to be in a 3-to-1 ratio, your M plus peak, your molecular ion, and then an M plus 2 peak. Right? This plus 2 represents, in both cases, the other isotope of chlorine or bromine. So we see 2 even peaks at the end for an M plus and an M plus 2 at the far right. We know that that molecule has a bromine in it if they're 1-to-1. If they're 3-to-1, we know that molecule has a chlorine in it. That's the isotope effect. All right, the final bit from mass spec that we're going to talk about is the nitrogen rule. The nitrogen rule says if you have an odd mass for your molecular ion, your M plus, your molecular ion, which is the farthest right peak in your mass spec, then if odd mass, then you have an odd number of nitrogens in that molecule. Now, it also means if you have an even mass, you have an even number of nitrogens in the molecule. And 0 is an even number, right? So don't try to find nitrogens or not. But if there's an odd mass for a molecular ion, then there's an odd number of nitrogens in the molecule. If you have an even, they have an even number of nitrogens. An even can also mean 0 nitrogens.